welcome to another video. We're going to be looking at the properties of the conjugate distribution function part 2. Now, the claim is that given some random vector x and the associated function, distribution function fx, and assuming the following condition holds, and it says that for all vectors a, b, which are real and n-dimensional, such that their entries satisfy this condition for all I in n. Right, so the third entry, say, is always larger in B than the third entry in A. And they satisfy this. So we have the sum iterating through 0 to n of the negative 1 raised to the power of k times of the other sum, where we have some vectors iterating through the following class, and I shall explain what it means in just a second, of fx of c, so the distribution function with the associated random vector x of this vector over which we iterate is larger than 0. Now, what do we mean by this? Well, the formal definition is as follows, like so. So we put it equal to the set of all those vectors with matching, whose dimension is n. So the first parameter, and it's the class of all those vectors which have precisely k matching entries. They can be any entries, right? So maybe if we say that we have a 5-dimensional space and that we are interested in the class of all those vectors which have 3 matching entries, it could be the first, the third, and the fifth. But then the second and the fourth must be different. So this is what we mean by that. And we can move on to the proof. So, the proof. We shall only prove the simplified version, so we shall assume with little loss of generality, so with a little loss of generality, log, assume that n is 2. In the case that n were larger than 2, we would use mathematical induction. And the proof is very technical, very complicated. We won't do it. We will just look at the simplified version. But the hardened one is analogous, in a sense. Now, alright, so with the view that n is equal to 2, we write that we have the outer sum ranging through 0 to 2 of the negative 1 raised to the power of k times the sum, where we have vector c iterating through the delta set 2k, right, where k is the index from the outer sum, fx at c, or of c. And now we can explicitly write this out because n is so small, so it's easy, right? So we come to the conclusion that this is equal to fx at b1, b2, or of b1, b2, so this is a vector, right, minus the distribution function of the associated random variable x of the vector b1, a1, a2, plus the distribution function of the associated random variable x of the vector a1, b2, closing bracket, plus the distribution function of the associated random variable x of the vector a1, a2. Right, now, but we can transform this, we can do better than this. So we understand this is equal, by shifting things around a bit, to the distribution function fx of the random vector b1, b2, minus the distribution function fx of b1, b2, minus distribution function of a1, b2, minus the distribution function fx of a1, a2. And lo and behold, perhaps a picture is in order. Right, so we will have the axes. So the y-axis and the x-axis. And thereon we have some 2 points. Right, so we have here a1, say a1, and b1 and b2. Like so. Okay, now I would just like to say a little word of warning. We don't know what the function fx looks like. This is just a little tool, little mnemonic device, right? Now, we say that the fx then is equal to this whole square. Like so. Now this rectangle corresponds to the term fx b1 b2, and we have the fx b1 a2, which corresponds to this rectangle. Right, so we are left with the rectangle up here, which we can describe using px, right, because that's the distribution associated with this distribution function, right? So we can write this as the distribution where the first coordinate is smaller than b1, meaning we are going along this axis. So we have that x1 is smaller or equal to b1. Now, of course, we have that x is x1, x2, right? This is our random variable composed of two random vector composed of two random variables. And the second variable is bounded from above and from below. So we have that a2 is smaller, certainly. We want this segment smaller than x2, and it is smaller than b2. Right, and we do the same trick with this term as well. So we get the picture will this time look something like this. So this time we have the right variable, the first coordinate, bounded from just one side. So we have x1 smaller or equal to a1. And now a2 is bounded from both sides. So we have a2 is smaller than x2, which is smaller than b2. Like so. Now, these two leave us only with this square. So jointly, this may be described as P of a1 smaller or equal to x1, a1 smaller than x1, which is smaller than or equal to b1, and a2 smaller than x2, smaller or equal to b2. But this is a probability, and as such, it is non-negative. And this concludes the proof.